Hi all, in this video we are going to discuss about the basic ER diagrams followed by the serialization techniques, whether from the given problem we are going to find how to find the given transaction using view serializable or the context serializable. Then we are going to discuss about the problems related to the dependency preserving and the lossless decomposition. Okay, so let us see one by one. Okay. Now so in this video, okay, the very first one is the ER diagram. Followed by the second thing is the dependency preserving problem. Third one is the lossless decomposition problem. And the fourth one is the view serializability. The fifth thing, conflict serializability. So these are the few things we are going to discuss. Okay. So let us look at the ER diagram first. So what is the meaning for this ER diagram? Which is nothing but the entity relationship diagram. Okay. So from the model key I have made the, so this is the question. What's the question here? So you are going to construct an ER diagram for a car insurance company whose customers owns one or more cars each. So when each car has associated with 0 or more number of recorded accidents, and each insurance policy covers one or more cars and has one or more premium payments associated with it, and each payment is for a particular period of time, set of customers, and the date when the payment was received. So these are all the constraints given. So in the ER relationship, first you have to represent, the first and foremost thing you are going to provide is the logical structure of your database. So what is the logical structure of your database? Then followed by, first you have to identify the customer entity. Okay. So what are all the entities you have to identify? Entities you are going to identify. So what is the first entity? It is the customer entity. So any car must be owned by some customer only, right? So the very first entity is the customer entity, and this particular customer entity may have the attributes. So the attribute represents what are all the values you can provide by means of using that particular as a table, right? So the customer, any customer may have the customer ID. So you can depict or predict this customer ID through the primary key constraints, then followed by the name attribute. So the name attribute is considered as the composite attribute here. So what is the meaning for composite attributes? So here the attributes may be further divided into n types. Number one is the primary attribute, where you can uniquely identify your data, followed by the second thing is the composite attribute. So any attributes when you can able to further divide means that will be considered as a composite attribute. Here any customers may have their first name, middle name and the last name. So here the customer entity, then inside my customer entity the name is considered as a composite attribute, then followed by the address, phone number, date of birth and the age. So these are all the few attributes of my customer entity. And similarly there is a car entity, accident entity, insurance policy entity. These are all the things that can be added by the user according to their perspective of viewing this particular database, right? Okay, then you have to specify the relationship in the ER diagram. This is the next thing. Okay, so you have to specify the relationships. So the relationship may be 1 to m, 1 to 1, 1 to many, many to 1 or many to many. This is the thing. So 1:1 relationship means a student must have registered a single department, right? It is 1:1 relation. And my student may have n number of subjects, and that n number of subjects can be belonging to one student. Then any projects, n number of projects can be assigned to n number of employees. That is the best examples of representing these types of relationship. And in the ER diagram you can specify all these types of relationship, right? Then followed by the diagram. This is the typical ER diagram of this. So the primary attribute, that is the prime attribute, that is the primary key, should be entered. If you want to represent the attribute, then you have to specify the oval symbol. The entity should be represented in a rectangular symbol, right? So the primary attribute is represented using the underline and the right? So here in my car insurance company, here the customer is having the customer ID as the unique name, so it is considered as the prime attribute. And for the car ID, insurance policy, the policy number, and for the premium payment I have made it the payment ID as my prime attribute. Okay, now after the prime attribute I may have the composite attribute, which may be splitted into n number of attributes, followed by my derived attributes, right? Derived attribute and the multi-valued attributes. So these two are the additional attributes. First one is the derived attributes, and the next one is the multi-valued attributes. So the derived attribute is when you can able to derive some value from another value, means that is considered as a derived value. From the date of birth you can derive the age of a customer, right? And multi-value means any customer may have more than one phone number. So these are all considered as the different categories of the attributes, followed by the other entities. And this is the relationship 1:n, meaning that one customer may have n number of cars, and n cars can cover, a single car can cover a single insurance policy, and that single insurance policy can have n number of premium payment. This is purely depends upon the user constraint. This is not restricted like this is like this. Okay, so according to my point of view, this is the ER diagram. Okay, owns, has, covers, pays, these are all the nouns representing the relationship between the two entities, and whether it is a partial participant or the total participants, you can represent in the ER diagram as well. Okay, now move on to the next question, which is nothing but what is my second topic, the dependency preserving. So the dependency preserving and the lossless decomposition problem are the typical problem frequently asking. So this is the question given. So check whether the relation R of A, B, C, D, E with the functional dependencies A implies B, C, D, B, C implies A, E, D, D implies E and C implies D, E. It is composed into R1 of A, B, R2 of B, C and R3 of C, D and E. Whether it satisfies the functional dependence decomposition and the lossless decomposition. This is the typical question. Okay. So now what is the constraint I need to check? So the dependency preserving is nothing but if you can able to preserve the dependency even after the decomposition made, then that is considered as a dependency preserving, right? So what it implies, so let us look into this. So look at this. I am in my original relation I am having the relationship as A, B, C, D and E. Okay, I didn't mention E. Okay, so it is decomposed into A implies B, C, D, B, C implies A, E, D and D implies E and C implies D. So it is further divided into 4 tables, right? So whether it is a dependency preserving or not, that I am going to check. So for that, first I am these are all the dependencies, and these dependencies, if you make the decomposition like R1 of A, B, R2 of B, C and R3 of C, D and E, if we can, after decomposing that, if you could able to preserve this functional dependencies again, then that is considered as a dependency preserving decomposition. That is the meaning for this. So now what is my first decomposition? I am going to decompose the entire table into three decomposition: R1 of A, B, R2 of B, C and R3 of C, D and E. Right? I have written like this: R1 of A, B, R2 of B, C and R3 of C, D and E. Now in my first relation, what's my first relation? A, B is my first relation. First I need to find the closure. So what is the closure? If I know the value of my left hand side, what are all the possible values I can able to derive? From the original relation you have to find. So if I know the value of A, I can able to derive the value of A again. Then B, C, D, right? Again, if I know the value of BC, here BC, I can able to find A, E and D. So A, D is already here, so I can able to find E as well. So A, B, C, D is my closure when I know the value of A, which means that, so you have to skip the extra attributes. So here R1 is having only 2 attributes A and B, so I can able to skip the remaining 3 extra attributes C, D and E. So A can functionally determine B. Again you have to find the B closure as well. The B closure, through by means of knowing the value of B alone we cannot able to determine anything. So B is the trivial functional dependency, so you are going to skip this. So what is the functional dependency of my relation 1, which is nothing but A implies B. This is the first answer. Then what is my second decomposition? R2 of B, C, right? So first I need to find the B closure. So B closure is by means of predicting the value of B, knowing the value of B, I can able to predict the value of B alone. So it is a typical trivial dependency. Then I need to check the closure of C. C closure is D and E, right? From this, if I know the value of C, I can able to determine D and E. If I know the value of D, I can determine E. So D and E is not at all in this relation. So F2 is having the null dependencies. Then followed by R3 we are having C, D and E. The C closure is by means of knowing the value of C, I can determine D and E closure is E alone, D closure is D, E. So if I know from this we conclude the fact that C implies D, E and D implies E. This is the conclusion. And what is my function 3 represent, the functional dependency of the relation 3 represents C implies D, E and D implies E. And if I made the union of all these things, so F1 union F2 union F3, if I can conclude the fact that the original dependency is preserving, means that is a dependency preserving. Now look, I am going to write all this. A implies B, followed by the null, followed by C implies DE, and D implies C. But here we are going to compare this with this. By means of knowing the value of A, I can derive B. Then C and D, that is not included in this fact. So look at this, BC implies AED is not in my decomposed relation, so it is not at all a dependency preserving one, right? So what is my conclusion? So after made the decomposition, if I can able to derive the original dependency by means of union, means that is dependency preserving. That is the meaning for this, right? So next move on to the next question, which is lossless decomposition problem. So here we are having three rules: rule number 1, rule number 2, and rule number 3. So what are the three relations? Look at this example. So first, what is my rule 1? The union of attribute must return the original one, right? So here union implies original. That is the first thing. What is the second rule? The second rule is the intersection of my relation should not be empty. Intersection not null. Okay. And what is my third and the last one is the common attribute. That is the intersection attribute must derive is the intersection one either derive the relation 1 or the relation 2 or the relation 3. That is the three constraints of the lossless decomposition problem, right? So the union of all the decomposition should produce the original one, and the intersection made by all the relationships should not be null, and the intersection one must produce one of the relations. That is the constraint. So let us look on to the problem. So from the same problem, I am going to split the relation into R1, R2 and R3. R1 is having A comma B, R2 is having B comma C, and R3 is having C, D and E. So look at this. What is my first rule? Says the union of the attribute is going to provide the original one. So the R1 A comma B union with R2 B comma C union with R3 C, D and E. So you are making the union of all this. So A, B, C, D and E. So that returns my original relation A, B, C, D and E. So the first rule gets satisfied. What about my second rule? Attribute of R1 when intersection with attribute of R2. Attribute of R1 is B, A, B. Attribute of R1 is A, B. And the attribute of R2 is B, C. And the attribute of R3 is C, D and E. So it is having the common attribute B and C, right? So second rule is also satisfied since it is not null. Then what's my third rule? The common attribute is either deriving the R1 or R2 or R3. What's my common attribute here? Either B or C. Either B can derive the attributes of R1, A or B, or C can derive the remaining relation. So look at this. By means of knowing the value B, I can derive A, not at all, right? Because B, C only derive A. So B implies A is not possible. So this is not possible. And C implies A is also not possible. Then move on to the next one, B implies BC. So relation 1 is not possible. What about B and C here? B implies BC, whether B implies C? Whether B implies C? B implies C? No. Then followed by C, C implies BC, C implies BC, now C implies DE. So R2 is also cancelled. What about the R3? C, DE, whether C can derive C, DE? Yes, C can derive DE. C can derive DE. So at least since one of the condition is satisfied, it is the last test. That is the meaning for this. Okay. So now move on to the third one, which is the view serializability and the conflict serializability. So I have made them. So first we look on to the conflict serializable one, then move on to the view serializable. Okay. So this is my fourth one and this is my fifth one. So what is the meaning for the conflict serializable and the view serializable? So what is the meaning for serializability? So what happens if your transaction is not in the serial order? If your transaction is not in the serial order means the interleaved transaction may get the false result. That is loss update problem and a temporary problem, overwrite problem and dirty read problem. These are all the problems we could lead if the transactions are interleaved. That is, one transaction is running at the same time. Since it doesn't finishes, it doesn't update its values. So if another transaction is trying to read the values before it writes up, then that will lead to conflicts. So for getting whether the serial is a conflict serializable or the view serializable, we have to check the conflicts. The conflicts may arise when at least one of the function is the writer. So either write conflict occurs or write-read conflict occurs or read-write conflict occurs. If at least one of the operation is the write operation, then there must be the conflict. So you have to find the conflicts among the transaction. So the most important thing is the conflict arise between different transaction. Note it down, different. You should not look into the same transaction. You should check about the. You have to check the different transactions and with the same data item. This is the thing you have to check. Different transactions, same data items. That is the thing. Okay. Now look into the concept. So first, how can you check it is a conflict serializable? First, before that, you have to draw the precedence graph. So for that, I have to understand the precedence graph. What is the meaning for precedence graph? Every graph must have the vertex and the edges, right? So in case of the precedence graph, you should make the edges from one vertex to another vertex if there is a conflict between the two transactions. So the number of vertex represents the number of transactions and the edges represents from where to where represents the conflicts between the transactions. So look at this. So here we are having the two transactions. This is the given transaction T1 and T2, and from the given transaction these are all the transaction details they have provided. So R of X, W of Y, W of Y, R of Y, R of Y. This is the transaction given as per the question. Now you are going to check whether it is a conflict serializable and whether it is a view serializable or not, right? Now for checking the conflict serializable, so listen, every conflict serializable is a view serializable, right? Every conflict serializable is a view serializable, but any non-conflict serializable is may or may not be a view serializable. It is not that every non-conflict serializable is not a view serializable as well. No, you have to check if in case if any schedule is belonging to a non-conflict serializable, then you have to check whether it is a view serializable or not. But in case if you know the schedule is the conflict serializable, you need not to check it is a view serializable, because by default every conflict serializable is a view serializable. Okay. Now given the transaction, so first I need to find the conflicts. So read, I am going to check here and here. Read and read is not at all a conflict. Then read write, so there is a conflict, but between the different items, right? Here x, it is y, so there is no conflict at all. Then write for the same data item, so there must be the edges between the transaction T1 and the T2. So I am going to draw the edge from T1 to T2. Listen, I am having two transactions, so I draw the two vertices and I am going to plot the graph from T1 to T2. Why I have made the graph edge from T1 to T2? Because I am having the conflict from T1 to T2. Then I am going to check W of R y with R of y. Yes, the conflict between the same data item. So transaction T2 to T1. Then R of y with R of y again. Read is not at all a conflict. So we made a conclusion that T1 leads to T2 and T2 leads to T1. So there is a deadlock situation, there is a cycle. So if your question is the schedule is a conflict serializable, then the answer is no. Why? Since the precedence graph is a cyclic one. This is a cyclic one. The above schedule is not a conflict serializable. So you have to check whether the graph is containing any cycle or not. Right? If it is a non-cyclic, means it is a conflict, and as a result it leads to view serializable. But it is not a conflict serializable since the graph is having the cycle. Now you are going to check whether it is a view serializable or not. Okay, the conclusion is not a view serializable, but how you are going to check now? So now, since it is a non-serial schedule, you are first going to convert this non-serialized one into a serialized one. Serialized means one complete transaction when over, then the second transaction is going to begin. So since the transaction T1 is having read of x, W of y and R of y, so I am going to write all this into a single one, followed by the T2, and I am going to write again R of y, W of R of y. Okay, and this S1 is corresponding to T1. When completes over, it is going to start the T2. Then S2, T2 when completes over, starting the schedule T1. So T2 is R of x, W of y and R of y. So here also R of x, W of y and R of y. And when T2 completes well, it is going to begin another transaction T1. Now for the case of view serializable, you need to check the three conditions: initial read, update and the final update. Right? So these non-cyclic. For the conflict serializable, as I not cycle in precedence graph. That is the thing. And for the view serializable, we have to check three conditions: number 1, 2 and 3. What is the condition 1? Initial read, update and final update. Initial read means without write. If any transaction is going to read the data item in the given schedule, then in the corresponding serial schedule also that transaction must have to read the same item. Update means whatever the item that is written by one transaction to that is read by some other transaction, then that schedule must be followed by the remaining given schedules. And the third one is the final update. So whatever the last write performed by the given schedule, then that transaction must have to perform the same last updation mode in the corresponding serial schedule also. look at this example, initial read, update and final update. So I am having two transactions, T1 and T2, and I am having two data types. So I have mentioned like this: S represent the given schedule and S1 represent the corresponding serial schedule 1, and the S2 represent the corresponding serial schedule 2. Now, so who is performing the initial read? So look at this, X is having the initial read done by both T1 and T2. Look at this. So before reading the value of X, I am not having any kind of write operation, so I have mentioned it as T1 and T2. Since R of Y is not having any initial read, so I have mentioned it as null. And similarly for this also, T1 and T2 is performing the initial read for the serial schedule 1, and here also the T1 and T2 are performing the initial read of X, and Y is same. So for the initial read, all are same. What about the update? So look at this, which one is writing, and that written content was read by which one. Here the T2 written content is read by T1. But wherever the write operation, so here is the last write operation, that is read by the T1. So the link is from T2 to T1. So here for the data item Y, so no X write, so I have made it as null for all this and for this. So what about this schedule S1? For the value Y, the transaction T2 written value is read by T2. So T2 implies T2 is not necessary. You have to check for the different transaction only. Since this is the last read, it is not performing as the given schedule. And what about the last one? Here also the read and write between the same transaction T1 only. So it is not at all equivalent to the first given schedule. So by means of comparing all this, we conclude the fact that since the given schedule and the corresponding serial schedule is not equivalent at all, we conclude the fact that it is not a view serializable. So look on to the same question for the schedule S2. Here we are having the three transactions, T3, T1, T1, T2, T2, T3. Okay. So first you are going to check whether it is a conflict serializable or not, followed by the view serializable constraint. Okay. Now look at this. So S2 is having these three things. First I am going to find the precedence graph. As I mentioned earlier, we have to find the conflicts. So read is not at all a conflict. Read, write, same transaction, need not to check. Write of Y, R of Z is not at all a problem. Read of Z, write of Z, same transaction, need not to check. Write of Z and read of Z. Yes, there is a conflict. So I am going to made a edge from transaction T1 to T3. So in my precedence graph, I am having the number of transactions T1, T2 and T3, and I am going to draw the graph, draw the edge from T2 to T3, from T2 to T3. Yes. So since it is an acyclic graph, yes, the given schedule is a conflict serializable since there is no cycle in my graph. Okay. So an additional question can be given like, what is the equivalent serial schedule for the given non-serial one? So if the question is like that, then you have to mention the equivalent serial schedule for this by means of removing the edges according to the count, outlet count of the schedule. So given that, so since T1 is not having any edge, the T1 may become as a first one or as a second one or as a third one, since we are having three transactions, right? Then there is a question whether T2 comes first or T3 comes first. Okay. Okay. Now the edges from T2 to T3, right? So only after completing the T2 we can provide the value to the T3. So the T1 may come either first or middle or last, but the T3 must come only after T2. So T2, T3, here also T2, T3, T2, T3. So there are three equivalents possible for the given schedule. Yes, by we already know the fact that since it is a conflict serializable, it is a view serializable one, but we are checking whether it is a view serializable or not by means of looking into this. This is my given schedule, and since I am having 3 transactions, there are 6 corresponding serial schedules possible, right? So according to the factorial, I am getting the value of 6 as either S1, S2, S3, S4, S5 and 6. So you can start either the transaction T1 in the middle, right? T2 as the first one, T1 as the first one, or T3 as the first one, followed by T2, T3, T3, T2, T1, T3, T3, T1, T2, T1, T1 and T2, right? So this is my given schedule and the corresponding serial schedule, yes, right? So this is the schedule, serial schedule for the transaction this. Then S1, S2, S3, S4, S5 and S6. So I am going to compare all this and I am going to perform the initial read, update and the final update similar to the same question. And I have concluded the fact that any serial schedule which is following this order is the thing which is the same as the given schedule, right? So these are all the important questions related to this, okay? And we are going to end up this video, right? Okay, let us make the final overview of the topic we have discussed today. So first we have discussed about the entity relationship diagram. We have first we have so we look into the concept of the ER diagram, followed by the attributes of your ER diagram, how to represent the relationship, then the decomposition preserving problem, the lossless decomposition problem, followed by the serializability and how to draw the precedence graph, conflict serializability and the view serializability. So these are all the topics we have discussed today. I hope you are enjoying this. Thank you. We'll see you in the next videos. Thank you.